Hello everybody, so today we are going to talk about intuitive symmetry. It's nothing, it's just about the normal symmetric and the regular shapes that we see, but we are going to use little of our intuition to make shapes more symmetric. So let's say I have a shape over here like this, and we know that if I fill that particular part using a straight line, the whole picture or the whole shape is going to be more symmetric and more regular, more geometric. Now let me draw some circles, and okay, here we have it. As you can see, if I fill that one circle at the bottom left, then the entire shape would look more symmetric than it was before. And how do we know that? It's because that's called intuition, and humans have it, we have it. And okay, so in what way is this useful for us? Is elementary particle physicists use this method to find new particles or the properties of new particles. So how do they do that? Let's take a look. Initially there were only 11 fermions, okay, and they are the electrons, muon, tau, and the respective neutrinos of the electron, muon, tau, and the quarks, the up, down, a strange, charm, and the bottom quark. So what people did was they tried to arrange these fermions in their increasing masses. So first they took this electron, muon, tau, and they arranged them in their increasing mass. Then they took the neutrinos and arranged them in their increasing mass. Then they took the quarks. And what eventually happened was they found groups. That is, the first group, which contained the electron, neutrino, and the up and down quarks, kind of a 4-member group. And even the second or the middle case of muon also followed the same rules. And the third group is kind of which has the higher mass compared to the other two, didn't fall into this particular category. So people thought, okay, there is something missing, there is a quark missing, because from the picture itself you can say we have an electron kind of thing, that is the tau with the negative charge. We have this neutrino, electron neutrino, same way we have a tau neutrino there. Then we have this up down quark, and in the second case we have the strange charm quark, but in the third case only one quark bottom. Where is the top? Yeah, so people try to then identify what could be its property, and that's where they added more details to these groups. They included the charges, and guess what, they found that every quark, every neutrino had no charge, and the up down quarks have 2 by 3 and minus 1 by 3 charge. Similarly, the strange and the charm has respective charges, and the bottom has minus 1 by 3. So our unknown particle should have a charge of 2 by 3. You know what happened later? They indeed discovered this top quark, and it did had a 2 by 3 charge and had higher mass compared to the other two groups, other quarks in the other two groups. Wow, that's something fantastic. And okay, this is just one example. Let's take a look at another one. Now they took a bunch of baryons with half spins, and I seriously, my intuition doesn't tell me why they chose bunch of baryons with half spins, because and maybe they might be working too long with the elementary particles, and somehow they saw, okay, if we take this group, we might find something, I don't know. So they chose a bunch of baryons with half spins, and which are they? And they are these protons, neutrons, and then we have this sigma with 0 positive and negative charges, kind of 3 flavors. And we have lambda with neutral charge, and we have xi with both negative and neutral charges. And apart from the charges, there is something called strangeness, or the strangeness quantum number. And what does it say? well, you can Google about it, but let's just uh, take these values into account for these elementary particles. And for proton it will be 0, and for neutron it will be 0. For sigma it should be -1, and for lambda 2. Then the xi, which has strangeness of -2. Something interesting happens when we try to plot the charges in the x-axis and this strangeness along the y-axis. So let's go ahead and do it. So strangeness of proton is 0, whereas the charge is +1, so it occupies the top right. And next we have this neutron, which has 0 charge and 0 strangeness, and follows the sigma, xi and lambda. So if we try to connect all these particles together, we get a nice hexagon shape, or kind of structure which is regular and symmetric. And let's say if we didn't discover xi 0, or the one in the bottom right, the particle that is in the bottom right, and if we didn't discover it, then from this particular structure itself we can say, okay, for these particles to form a regular symmetric geometric shape, then this hexagon is the only way. Then the missing point of the hexagon represents a particle, and that particle has a property of zero charge, and has a strangeness of -2. Thus we have deduced a particle's property which is not even discovered. Thus we can do it. But it's not the case in ours, because we have already discovered xi with neutral charge, that is with 0 charge. So you can try this on different sets of mesons, baryons, and come up with new particles in future. So is this the only way to connect all these particles and create an hexagonal shape? Is hexagonal is the only shape we can get from these particles? Needn't be, because you can even form square like this. And we might say, okay, we are a particle missing, that is a particle with 0 strangeness and negative charge, and a particle with -2 strangeness and a positive charge. And I think the one in the top left is electron, and because electron might be a candidate, but it's a lepton, not a baryon. So but it doesn't matter, because we haven't found such kind of particles as of now, so let's stick to the present. So all the credit goes to Emmy Noether from Germany, who is a mathematician, actually discovered that if there is a conservation theorem, then there is symmetry. Now you can go ahead and read more about that. And happy elementary particling.